I want to welcome all of you here this evening. My name is Ralph Cavanna. My role will be to provide a brief introduction to the speaker, but you're now here in the midpoint of the 5 public lectures by our current MING visiting professor on energy and the environment. Monday and Tuesday were on buildings and industry and Amory's continuing exploration of energy efficiency, opportunities, technologies, policies, barriers. Tonight he'll take on transportation. And in telling you a little about him, I face the challenge of introducing one of a handful of international celebrities who is instantly recognizable by his first name. And I thought that I would rise to that by simply telling you a story about Amory and the transportation issue. The Rocky Mountain Institute, which has many friends in this room, was founded 25 years ago, I want you all to remember. And when it was founded, its principal signature issues were really the issues that Amory covered in his first 2 lectures on Monday and Tuesday: energy efficiency in buildings and industry. The Rocky Mountain Institute had vehicles. It had a really nifty building. The vehicles were, to be kind, unexceptional. One of the RMI founders routinely drove around in a Ford 150 pickup truck, which Amory somewhat defensively, I thought, once described in a published interview as, quote, surprisingly efficient, unquote. But again, this was not their strength. And then in 1991, something important happened. The National Academy of Sciences was directed by the Congress of the United States to explore the technical potential for improving the fuel economy of passenger vehicles, about which nothing had been done basically since 1975. And the Academy decided to have a kind of science trial at its facility in Irvine, California. This was put together rather quickly, over a period of less than a month. The anti-fuel economy side was represented essentially by the world's automakers, who assembled their general counsels and their senior scientists, a formidable array, a small army of experts bristling with credentials. The pro-fuel economy side had none of that, and lacking anything else obvious to do, we of course called Amory. This was a preposterous thing to do. Amory had no formal training or visible credentials in this area. Amory had less than 1 month to prepare. Amory appeared, and essentially over the course of a week, in something that I really wish all of you could have seen, took on the assembled experts and general counsels of the world's auto industry and brought them to their collective knees. They were, of course, wholly overmatched. They have been wholly overmatched ever since, except recognizing this, most of them have now hired Amory to assist them in what I think all of us can see, well, all of you will be convinced by the end of the evening, is a vastly more hopeful future than the one we were confronting in 1991. Amory will now provide for you an updated version of what some of us saw for the first time in 1991. You're in for a treat. Amory Lovins.
Through Ralph's invitation to that event that I fell in with the industry. GM's head of advanced engineering was sitting in the back at that event. He was interested in my ideas. We had lunch. On a handshake, he brought me into Design Studio to see the still half clay ultralight concept car, which was pretty much what I'd been talking about. And there followed an interesting relationship in which for a couple of years GM graciously took my car education in hand. I gave them a bunch of good ideas. And when it became clear that it needed a broader stage, I then took what had turned into the hypercar concept. I put it in the public domain so nobody could patent it. Fomented lots of competition in exploiting its commercial advantages, thereby amplified our $3 million R&D investment by a factor of roughly 3,000, and things have been pretty busy since then. Now, let me start just with a benchmark number from my colleague, retired Navy nuclear subcaptain Scott Pugh. He points out that the cubic mile of oil that the world consumes each year, 85 million barrels a day, can actually be visualized, and not just as a cubic mile. Another way he suggests to do it, because you can't really visualize 85 million barrels of oil, but he says take a barrel, it's 20 inches in diameter, it's 30 inches high. Now, lay it down on its side, put 85 million of them end to end. They will stretch 1.5 times around the world at the equator. And now take out all the ends, so it's simply a 20-inch pipeline 1.5 times around the world. And to get 85 million barrels to flow that distance in 24 hours, they have to be going at Mach 2, twice the speed of sound. That helps you visualize that much oil flow. And this naturally gives rise to various problems. So a lot of unlikely folks have been popping up lately to say we got to do something else for many good reasons. But I want to start with a little bit of economic history. In 1850, the fifth biggest industry in the United States was whaling, and most houses were lit with whale oil. But as whales gradually got shy and scarce, and first the sperm whales and then the other kinds started to get pretty hard to find, the price of whale oil drifted up, eliciting competition from a lot of things, but most of all, oil and gas, both made at the time from coal. Remember, this is long before Edison's electric light. And in the 9 years before Drake struck oil in Pennsylvania in 1859, that competition grabbed away from whale oil over 5/6 of the lighting market. The whalers were astounded to run out of customers before they ran out of whales. They hadn't been paying any attention to the competition. They were soon reduced to begging for federal subsidies on national security grounds, and the remnant whale populations were saved by technological innovators and profit-maximizing capitalists. Now, this is a little like where we are today with oil. To be sure, the time constants are smaller. It isn't just a matter of an easy screw-in retrofit to change your your whale oil lamp to a coal oil lamp. But we have vehicle fleets that take longer to turn over. Nonetheless, the same basic dynamic is at work, because we've spent several decades now amassing a huge portfolio of very powerful technologies for saving oil and substituting for oil, and no one had bothered to add them up before. But when my team did in 2004, we found that they were more than enough to replace all the oil that we now use in this country at roughly a fifth the cost of buying it at today's price. Assuming its externalities, its hidden costs, are worth zero, a conservatively low estimate. So my wildcatters have been out drilling lately, and they found 8.3 million barrels a day in an undrilled play under the Detroit Formation. And they found 1.6 million barrels a day in heavy trucks, and 1.2 in industrial fuels and feedstocks and so on. Altogether, a huge amount of negabarrels down there, savable oil, plus a big play in robustly competitive biofuels, and 12 trillion cubic feet a day of gas that we found in places like air conditioners. More on that later. So shouldn't we drill the most prospective plays first? I mean, wouldn't it be kind of embarrassing to go to the ends of the earth to drill for very expensive oil that might not even be there, and somebody else finds all that oil lurking under Detroit? So in 2004, we published a detailed study that's independent and peer-reviewed. All the numbers are clearly laid out. Nobody's argued with it. And it was co-sponsored by the Office of the Secretary of Defense and the Chief of Naval Research, written for business and military leaders, not for politicians. They can hear about it in due course from their constituents. And we built the argument around competitive strategy business cases for cars, trucks, planes, fuels, and military. You can get the whole book and all its 24 technical backup annexes free at oilendgame.com. And its thesis is arrestingly simple, that over the next few decades, say by the 2040s, this country can eliminate its use of oil and have a much stronger economy, and that transition will be led by business for profit. Here's what it might look like. The upper red curve is the use of oil, the lower dashed red line is the imports of oil to the United States, and in the official forecast they keep heading toward the northeast corner. But we showed how to turn these curves downwards along the green curve by redoubling the efficiency of using oil, already doubled since 1975. And it turns out that in year $2000, the cost of saving a barrel would average $12. Then we could turn down steeply along the blue curves by replacing the other half of the oil at an average cost of $18 a barrel with a mixture of saved natural gas and advanced biofuels, mainly cellulosic ethanol. Now, we know this sort of thing works in principle because we've done it before. Look at this even steeper drop the last time we paid attention to oil, 1977 to 85. In those 8 years, GDP grew 27%, while oil use fell 17%. Oil imports fell by half. Oil imports from the Persian Gulf fell by 87%, and it would have been gone in one more year if we'd kept that up. In fact, the world saved so much oil so quickly that it cut OPEC's exports in half in 8 years, and it broke their pricing power for a decade because we customers turned out to have more market power than the oil supply cartel. We, especially in America, the Saudi Arabia of negabarrels, could save oil faster than OPEC could conveniently sell less oil. Well, that was then, this is now, you are here, but we could run that old play all over again a lot better with today's much more powerful technologies. Now suppose that from now till 2025, we were to invest $180 billion once, half of it to retool the car, truck, and plane industries, half of it to build a modern biofuels industry. And suppose that that so softened the world oil market, as it well might, that the oil price went down to $26 a barrel, which was indeed the official forecast when we were writing the book. But against a $26 oil price, that $180 billion investment would be saving $155 billion a year gross, $70 billion a year net. At the same time, as a free byproduct, it would cut America's CO2 emissions by 26%. It would get us 1 million new jobs, mainly in rural and small town America, doing the biofuels. And we'd get to save 1 million jobs now at risk, mainly in automaking, where we have a really simple choice. Do we want to keep importing efficient cars to displace oil, or do we want to make efficient cars and import neither the oil nor the cars? That somehow sounds like a better idea. We found the business case for these actions is so compelling that this strategy could be implemented without new fuel taxes, subsidies, mandates, federal laws, or anything else either party doesn't like or could mess up. That is, such public policy as is desirable to support rather than distort the business logic could all be done administratively or at a state level. Now, technologically, the nub of the problem is, of course, transportation. Vehicles use 70% of the oil. But we found that a common technological strategy of low mass, low drag, and advanced propulsion could triple the efficiency of cars with a 2-year payback, trucks with a 1-year payback, and planes with a 4 or 5-year payback. Often with improved performance, for example, this Opel carbon fiber diesel hybrid Eco Speedster would get 150 miles an hour and 94 miles a gallon, although not at the same instant. And the surprise to many is that the ultralighting that doubles the efficiency of these carbon fiber concept cars is free because the costlier materials, as I'll explain, are paid for by simpler automaking and a 2 or 3 times smaller propulsion system. There are, of course, other big savings in buildings and industry, but I've talked about those the last 2 nights and won't revisit them here. Let me concentrate just on cars, then on trucks and planes. And the technology for all of these kinds of efficiency is continuing to improve faster than we use it up, so that efficiency, unlike oil, is an ever bigger and cheaper resource. Of the projected increase in the use of oil in this country to 2025, 70% of it is from light trucks and heavy trucks. So you won't be surprised that I'm going to say a bit about both of those. You can see the use projected for cars is essentially flat, and the second biggest growth area after trucks is air travel. Now, Just a word on basic automotive physics, because I know there are a number of engineers and physical scientists in the House. The powertrain efficiency from the fuel in your tank to the wheels of a car or light truck is the product of the fuel to work efficiency of the engine times the work to output torque efficiency of the mechanical part of the engine as opposed to the thermodynamics times the driveline efficiency in transmitting torque from the engine to the wheels. And with an auto engine running on gasoline as opposed to the somewhat more efficient diesel, this works out to about 17%, although a modern Prius hybrid does about twice that well if you drive it properly rather than the way Consumer Reports says to. Now, the vehicle load, what it takes to move the vehicle, technically known as the tractive load, is almost all of the energy that you have to get out of the fuel, but a few percent is to run accessories, air conditioning, lights, entertainment, and so on. And the tractive load, in approximate terms, in instantaneous mechanical power, has 4 elements. The inertia is what it takes to accelerate the car. That depends on its weight. It's F equals ma. The rolling resistance experienced by the tires, that again depends on the efficiency of the tires and how hard you press down on them, which again depends on weight. Aerodynamic drag rises as the cube of speed, and if you're climbing a hill, then you have to allow for that too. I'm going to neglect it from here on the assumption that uphill and downhill balance over time. And actually, both the inertial and the grade loads can be negative if you go downhill or you decelerate, and a Prius, for example, recovers 2/3 of that, or recovers that energy with an efficiency of 2/3 from wheel to wheel. Now, it only takes about 6 mechanical kilowatts of tractive load to run a Taurus, which is equivalent to 2/3 of a gallon per 100 miles. 100 miles per 2/3 of a gallon, that's awfully good. But you have to divide by this powertrain efficiency, so it's 6 times worse than that. And the important thing to remember about this physics lesson is that you cannot make the powertrain more efficient than 100%, but you can reduce the tractive load almost without limit by making the car lighter and more slippery. A lot of jurisdictions are asking us to reduce it considerably. If you look at the grams of carbon dioxide per kilometer emitted by a car, U.S. efficiency standards, if converted to that interpretation, are almost static, although California is trying to improve them radically, but not yet as radically as, say, China, let alone Europe or Japan. By the way, a Prius is down here. Notice the broken scale, that's 100. And I think the U.S. laggard position comes about from the basic assumption held by most people who make cars or car policy that to make cars efficient, they have to be squinchy, unsafe, sluggish, costly, ugly. You wouldn't really want one. And then the government has to induce you to buy this compromised vehicle anyway through either efficiency standards or high gasoline taxes. And of course, the titanic lobbies behind these two positions, automakers favoring high gasoline taxes, oil companies favoring high CAFE standards, have battled each other to a draw for over 20 years. But there's another way to think about technological change. How many of you still buy phonograph records as opposed to digital media, or cathode ray tube televisions instead of flat screens? You see, when you improve the technology enough, you can do an engineering end run around normal considerations just by redefining market expectations. So you'd want to buy the super efficient car, efficient as a byproduct of breakthrough engineering, because it's better, not because it's efficient. And that would give the automakers a much more robust business model, because they would only need to worry about competitive superiority rather than about random variables they can't control, like oil price and public policy. So to see how to do this, let's just look at the physics of where the gasoline energy goes, bearing in mind that your car every day burns roughly 100 times its own weight in ancient plants. Well, 7/8 of that precious energy never gets to the wheels. It's lost in the engine, idling, driveline, and accessories. Of the 1/8 that does reach the wheels, half of it either heats the tires and road or heats the air that the car pushes aside, and only the last 6% actually accelerates the car and then heats the brakes when you stop. But since only 5% of the mass you're accelerating is you, the other 95% is the car, only 5% of 6%, or 0.3% of the fuel energy ends up moving the driver. After 120 years of devoted engineering effort, this is not very gratifying. However, the good news is that 3/4 of the tractive load, what it takes to move the car, is caused by its weight. And every unit of energy you can save at the wheels will save an additional 7 units of energy you don't need to waste getting it to the wheels. So there's big leverage in making the car a lot lighter weight. That's not where we are headed because we forgot what Henry Ford told us about weight may be desirable in a steamroller but nowhere else. The most beautiful things in the world are those from which all excess weight has been eliminated. Whenever anyone suggests to me I might increase weight or add a part, I look into decreasing weight and eliminating a part. So if we find the way backward to Henry Ford, we'll have a lot of wisdom to work from. And we have a lot of relearning to do because here's what's been happening to the weight of cars sold in the United States, cars and light trucks actually. They now average over 2 tons. And we even looked, thanks to our analyst Laura Schul, at something I hadn't seen graphed before, which is the density of cars and vans, namely their curb weight divided by their interior volume. You notice it's been going up. Density? How does that help anything? And 70% of this increase in weight that we're seeing is due to design and materials, only 30% to changes in the size and the mix of vehicles bought. Well, if you want to make cars lighter to capture the basic physics advantage, there are 3 broad things you can make it out of. Light metals like aluminum, which are perfectly feasible, a bit more expensive. New generations of light steel, special alloys, and heat treatment. Or the strongest and lightest solution, advanced composites, reinforced, for example, with carbon fiber. That's what this handmade SLR McLaren from Mercedes is made of. It happened to get T-boned by a Golf, which was totaled. All that happened to the McLaren is it popped off a side panel, which they'll pop back on and fix the scratch later. But if you were to look under the hood, you would find at the front corners there's a pair of about 7.5 pound woven carbon fiber crush cones. And to crush these down into a kind of a plastic cow patty takes so much energy that these cones, weighing only 0.2% as much as the car, can absorb the entire crash energy of the car hitting a wall at about 65 miles an hour. That, by the way, is with a thermoset composite, like epoxy, which absorbs only half the crash energy per pound of a thermoplastic composite, which I'll be talking about. That absorbs 12 times the crash energy of steel per pound, and it does so more smoothly, so you can use the crush length or stroke up to twice as effectively. So with such magic strong but light materials that decouple size from weight, you just solve the safety riddle. That is, you can make cars big, which is protective and comfortable, without also making them heavy, which is hostile and inefficient. Therefore, you can save oil and lives and indeed money all at the same time. Anybody who follows the Formula One race world knows about this. Here's a shot of Catherine Legg running into a wall in an ultralight carbon fiber car at 180 miles an hour. By the way, her car is made of epoxy carbon or thermoset, which is subject to brittle fracture, and it's not nearly as tough as our thermoplastics. But, you know, that's not very promising with a person in there.
And the best news is that Catherine Legg has walked out of the medical center under your own power. How are you feeling?
A bit shaken, but I'm okay, as you can see. Oh, sorry. All my bits are intact, so it's good. Goes to show how strong the cars are.
Where do you have some injuries?
Oh, I just banged my knee. Car upside down, you bang your legs on the bulkhead and on the steering column and stuff, so just a bit of bruising, which won't look too attractive in my dress in the Atlantic's banquet tonight, but...
So, and in fact, Tom Friedman, in a film called Addicted to Oil on the Discovery Channel, was playing with some of these materials in the lab of a little company called Fiberforge that spun off from RMI. And first of all, he took the most complex and highly loaded body part, and, well, we've lost our sound, and showed that he could lift it with one hand.
I can't lift this.
Sure you can. It's not steel, it's carbon fiber.
Whoa! I'm strong, I'm not that strong.
And then he tried to do some damage to this piece of material, which is actually tougher than titanium.
So here's the part we just formed, Tom. But once it's trimmed, it can look just like these other parts.
You say these things are tough, right?
Oh, they're very tough.
You're gonna see just how tough. I'm gonna break one of these. Just plastic.
You want to try jumping on it?
Sure.
Here, why don't you try jumping on it on the floor?
Somebody got a bigger hammer? Here, give me that. Darn it.
So you can see that plastics have changed since the graduate. Now, even with old materials, with cars made of steel, by the way, the nationwide data confirm that size makes you safer, weight doesn't. You've probably seen a lot of press reports of government studies saying that if you make cars 100 pounds lighter, you'd kill hundreds or over 1,000 more people a year in the U.S. But that analyst assumed that size and weight are equivalent. He only looked at weight and assumed that size came along for the ride. But actually, some other analysts using exactly the same database teased out size from weight and found that if you made the cars longer at the same weight, if you made the cars shorter at the same weight, if you reduce size, you would kill more people. But if you made the cars lighter at the same size, you would actually save more lives. Very clear result. And therefore, making cars bigger but lighter with strong materials and integrative design is the way to save lives and fuel. Now, the problem with these advanced composite materials has always been cost. We use them a lot in military and aerospace at about 1,000 times lower production volume and higher cost than you would need for ordinary cars. In fact, the advanced composite market in the U.S. is about as big in tons as the chocolate market. This is pretty specialized stuff. But then I got encouraged about maybe bridging this cost gap when I met a young engineer at the Lockheed Martin Skunk Works, where they make the not quite impossible military aircraft. And he had led a team that in the mid-90s had designed an advanced tactical fighter plane airframe that was 95% carbon, 1/3 lighter, but 2/3 cheaper, because it was designed to be made optimally out of carbon, not metal. Well, it was so weird he couldn't find a military customer for it, so one batch later I was able to hire him to lead a similar effort for cars, which we did. And the result was an uncompromised, competitively priced, 3.5 to 6 times more efficient midsize SUV, done as a virtual design with 2 Tier 1 partners in Europe in 8 months in the year 2000 for about $3 million. And here's what it looks like. This is a 5-seat, mid-sized suburban assault vehicle, weighing a little less than half as much as the equivalent steel vehicle, because it would be made out of carbon fiber composites. 0 to 60 in 8.2 seconds, 114 miles a gallon on hydrogen fuel cell, or if you ran it on a gasoline hybrid like a Prius engine, it would do 0 to 60 in 7.1 seconds and 67 miles a gallon on gasoline. And that version would have an extra sticker price of $2,500, as we ascertained from actual bids for parts, as I'll tell you later. That would pay back in under 2 years at U.S. gasoline prices. So this was production costed, manufacturable, and it can look like whatever you want. This is what's called in the trade the active outdoor lifestyles Gen X, Gen Y crossover vehicle at a time when crossover vehicles were kind of a gleam in the eye. Now there are a lot of things on the road that look very much like this. We're flattered. If you were to fold down the right seats instead of the rear seats, it gets so cavernous you can put in 2 full-sized kayaks and 2 people. We'd prefer to control and steer it with a right or a left side stick, or if you're British or Japanese, you can stick them on the right. There's a virtual display, everything by wire or by fiber, all functionality in software. It's a computer with wheels, not a car with chips. Sony PlayStation 10, way cool. But it has some other interesting attributes. I mean, if all U.S. cars were this efficient, cars and light trucks, it would be like finding a Saudi Arabia under Detroit. And worldwide, the potential from this kind of efficiency is as much oil saved as OPEC now sells. So that's a big deal. And again, to get back to the physics, an ordinary car takes about a liter of fuel to drive 12 kilometers on level city streets, but you see only, in this case, about 12% gets to the wheels. Now, the industry has always focused on the losses, 85% loss or so, in the powertrain for the same reason Willie Sutton robbed banks. He said that's where the money is. This is where the losses are. But you'll appreciate from the last 2 nights' lectures where I've emphasized the compounding savings from starting downstream that we should really start at the wheels, because every unit of energy we can save at the wheels is going to save about 7 times that much fuel in the tank by turning those compounding losses left to right into compounding savings right to left, just as in the pumping diagram I showed last night. And it's pretty straightforward, even with a doubled efficiency powertrain, where that's only a factor of 3.5 gain, not 7, to get a tripled efficiency car this way. Of course, to get the real weight savings like this, you need to multiply weight savings and make them snowball. It used to be that you just do this once. You would make the car as light and slippery as you could think of, so you need less power to run it, and that lends itself to a smaller propulsion system, maybe with new technology, and the chassis parts like brakes and suspension get smaller. And because those things are all smaller, you can have more crush space in the same size car, more space for people and cargo as well. But you might think it costs more for all the obvious reasons. What we do, however, is work the design cycle, or as they say in naval architecture, the design spiral. You go around this loop a few more times, and as you do so, you start multiplying weight savings, because you're not only making parts smaller for lower mechanical loads, you're getting rid of a lot of parts. In a good hybrid, you may, for example, eliminate things like transmission, clutch, flywheel, axles, differentials, drive shaft, universal joint, starter, alternator. They just go away with their weight. Therefore, you get these nonlinear jumps in weight savings. And by the time you get through, you're using so little of the costly light materials, such a small powertrain, and you save so much money in simpler assembly and getting rid of parts and systems that you get a very reasonable and maybe even a lower cost. By the way, if you were wondering how that particular design does in a crash, this is 35 miles an hour into a wall, and you'll notice the whole front end crushes down, so you'd have to replace that, but there's no significant damage, no structural damage to the passenger compartment. Or if you run into a steel SUV twice your weight, each going 30 miles an hour, combined speed 60, you would still be protected from serious injury according to these simulations. I'm not sure there's any car on the road that does that. Now, that's all possible because of an ultralight composite body, which in this case also has an aluminum drop-in subframe in the front, so that we can use a variety of propulsion systems and have them all fit the same hard points and have a more easy to analyze front-end crush behavior. And this body is incredibly stiff, stiffer than practically any sports car, so it would handle extremely well, and it's designed for an extremely long life, doesn't dent or rust or fatigue, and if you ran into somebody in the parking lot at 6 miles an hour, it would be a fender bouncer, not a fender bender. Now, the really fun part is how you make this body. You notice, first of all, that its heritage is that of an airframe. It's suspended from rings rather than built up from a tub, which is our horse and buggy legacy. So it's extremely strong and stiff. And each of those parts, other than the floor tub, can all be lifted with one hand and no hoist. In fact, the biggest part here on the side that Tom Friedman was lifting, I've been able to lift with one finger. Each part is made with one low-pressure die set. In a steel body, you'd have 10 or 20 times as many parts, each with an average of 4 progressive steel stamping die sets. So you just saved about 99% on the tooling cost. And the parts then snap precisely together like a kid's toy for either gluing or non-adhesive thermal bonding. And because they fit together and align themselves, you don't need the jigs, robots, and welders normally needed to assemble and spot weld the body. And if you lay color in the mold, you get rid of the paint shop. So you end up with at least a 2/5 lower capital cost than the leanest plant in the industry. And the plant's smaller. In fact, the optimal size, around 50,000 a year, almost exactly matches the average nameplate production volume in this country. Now, there's been rapid progress with these kinds of materials. BMW has 60 specialists in Landshut who have bought the world's biggest resin transfer molding press, probably not for amusement. And they said in 2000 it would take them maybe 5 years to get their carbon fiber concept car into series production. It seems to be taking a bit longer, but they're already making over 1,000 a year of various parts for high-end models, and their website praises carbon composites in quite un-Germanic language. Honda and Toyota put their best automotive innovators in charge of their respective carbon fiber airplane businesses. Now, why do you suppose they would do that if it's all about airplanes? Ford has demonstrated remarkable capabilities in the GT with carbon fiber composites and combining them with light metals. And FiberForge, a little spin-off in Colorado from Rocky Mountain Institute, has come up with a process I'll show you videos of in a moment that uses kind of a digital inkjet printer to make a carbon and thermoplastic like nylon plywood. This is from a 1 square meter piece, uniform to better than 10 microns in thickness. And then it's thermoformed to net shape on a half-minute or 1-minute cycle time, matching the pace of an auto assembly line. So you get 80 to 100% of the performance of hand layup aerospace composites at 10 or 20% of the cost, and with very interesting economics, which have caused a number of automakers and tier ones to become customers. And meanwhile, the company's making things like backpack frames. That's a car seat for a tier one, Johnson Controls, shown at the Detroit Auto Show. And the first step is to make this tailored blank, which combines layers of carbon and or other fibers. For example, you can cut the cost very substantially if you have carbon layers around a cheaper glass center. And this is all run straight off a CAD drawing. And you can make variable thickness parts, different thickness in different places. I've lost the sound again. But I guess hearing the machine will not tell you a whole bunch about it. But it's laying carbon pre-preg and semi-preg tape, and ultimately could be able to lay raw carbon fiber and thermoplastic at about 1.4 meters a second, and then it'll become faster. So because you can control exactly the direction of the fibers in different layers, you can make the strength and stiffness match the load path. So if you want to make that car seat, for example, your computer analysis tells you you need different layers with fibers pointing different ways, and then you make it on the machine to a tailored blank, and then you form it in the next step into the shape you want and into the finished part. So this bowl sample, for example, was made out of a flat piece like this, which could even have non-uniform thickness, thinner in the middle than at the edges. Now, the molding step is quite straightforward, and for ease of visibility, we'll show it here with a fiberglass instead of a carbon fiber part because it's easier to see white than black. So when you've made your tailored blank, you just shuttle it into the oven where it's heated with an array of programmed Wendy's heat lamps. And when it just starts to droop a little from heat, because the nylon or whatever is getting soft, then you shuttle it into your press where you squash it onto a hot die. And the fibers flow where they're supposed to, and then you quench the die by passing cold water through it. And about a minute later, the roast is done, so you reach in with your oven mitts and take it out of the oven, and you trim off any loose bits you don't want, which in this case we weren't at pains to minimize because this was a cheap material, and then you're left with your finished part, and it's that simple. So very high materials efficiency, low scrap, and so on. Now, so far, it will, I think, have become clear that there are some Zen riddles here around making cars. Like big fuel savings can cost less than small fuel savings. You can tunnel through the cost barrier through integrative design. To leap forward, think backwards. Start at the wheels and think back toward the fuel tank. This one is like the Taoist remark that by doing nothing, nothing will be left undone. If you set out to save fuel, you will probably make incremental savings slowly at some extra cost. But if you set out to make a breakthrough integrative design of a car, you'll save a lot more fuel as a byproduct. And of course, to make cars cheap, you should use costly materials. And to make them safer, you should make them a lot lighter. And to get the best cars, just let the engineers go at it. So you get an automotive leapfrog. Now, to find out what it would cost to make such a car, FiberForge had its Tier 1 partner put out the design at almost a 500 line item level of detail in anonymous cost packs to the industry to ask what would the supply chain charge to make $50,000 a year. And from that, we learned that the extra cost of ultralighting the car is absolutely trivial. In this case, it's a 1.6% price increase at retail. That's down in the noise. If you made it a gasoline hybrid, it would cost about $2,500 extra because it's hybrid, not because it's ultralight. If you made it a hydrogen fuel cell car using rather expensive fuel cells by present standards, then it would save not 72 but 83% of the gasoline. But it would still be like buying gasoline at about $2.11 a gallon, which isn't such a bad deal. So if you look at the extra retail price you have to pay for the car versus how efficient it is, we're used to seeing from the National Academy curves showing that you can save a significant amount of energy at a modestly extra price. Some other folks thought, with a better track record, thought you could do better. And we did look at incrementally improved Academy mobiles that would save about a quarter of the fuel and pay back in a year or so. But then we said, wait a minute, suppose we start with a Prius propulsion system at 2004, or what Toyota then projected as 2007 prices, which have turned out to be true. And now let's put it in an ultralight slippery carbon body for a light truck or a car. The car gets about 92 miles a gallon instead of 55 for the Prius. In other words, almost doubled efficiency, but we're going to the right, not up to the right. The car costs essentially the same. This whole design space on the right, the ultralight space, does not add cost because, again, the cost of your materials are offset by simpler manufacturing and a 2 or 3 times smaller propulsion system. Now, there's a backstop technology in case the composites are not ready for prime time, and that's good because I'm materials neutral, and I happen to think composites are a good bet strategically for a bigger leapfrog because of their strategic advantages in manufacturing, but the market will sort out what materials win, and one of those could be ultralight steels. The steel industry says that they can make a, say, Taurus class vehicle at no extra cost with a 5-star crash rating, twice as efficient, by taking out a lot of weight. And if you then put a Prius-like hybrid powertrain in that at 2007 prices, it would save 80-odd% as much fuel as the carbon version at lower cost and at roughly a comparable cost per gallon saved. So it would be quite a worthy competitor. And since everybody knows how to make cars out of steel, this at least can give us assurance that we will be able to get most of those fuel savings one way or another. In fact, light steel is what some innovators in Munich used to figure out a 2+2 seat sports car, quite lightweight, very good aerodynamics, and without a hybrid but with a turbo diesel, they felt that they could get very good Autobahn high speeds and yet very good miles per gallon also, 87 or 157 in the two models, and it would sell for about 11 to 15,000 euros in 2009. Watch this space. Now, the automotive revolution then can start with an excellent hybrid, properly driven, that doubles efficiency, a good deal more if new diesels turn out to be able to keep up with ratcheting air quality rules. If you make it ultralight with better aerodynamics and tires and integrative design, you roughly redouble its efficiency. If you run it on, say, 85% ethanol, preferably from cellulose, you quadruple its oil efficiency again. So far you've saved a factor 16 on oil per mile, and you could actually use the biofuels if properly produced as a way to take carbon out of the air and put them back in tilth where they belong and pay the farmers for that. Now, a good plug-in hybrid, and they may be coming at us sooner than we think, can redouble or better fuel efficiency again by substituting cheaper electricity for ordinary shortish trips. And if you make the power grid set up so that it can buy the distributed storage capacity of the batteries and maybe even own them as a utility asset, then that could be attractive economically, and that's a precursor of the vehicle-to-grid fuel cell play with power plants on wheels. Now, so far, these stages of development can save 97% of the oil per mile that we use now, and of course, hydrogen fuel cells can also be competitive once you have such efficient cars and can act as very good power plants on wheels and can displace the E85, so they'll get to compete with biofuels and with plug-in hybrids. And hydrogen does actually become a serious competitor when the car gets that efficient. Here's the packaging diagram for that SUV, which takes only a third the normal power to run it. In fact, you can cruise it at 55 miles an hour on the same power to the wheels that a normal car uses on a hot day to run the air conditioner. So with these small hydrogen tanks, which leave plenty of room for people and cargo, you get a normal 330-mile driving range. You don't need any breakthrough in storage. You don't need ultra-high pressure tanks. Moreover, the fuel cell gets very much smaller, 3 times smaller, so you can pay 3 times more per kilowatt for it. So at a normal assumption about cost versus volume called an 80% experience curve, you would need 32 times less production volume to get the price down to a competitive level, and that'll cut a decade or two off the deployment time. Exactly the same logic, by the way, applies to hybrids, plug-in hybrids, and battery electric vehicles. Whatever your expensive propulsion system is, you'll need several times less of it, so its economics and packaging will become that much easier. And if you just compare, say, this fuel cell design at 35 kilowatts with the much higher fuel cell requirements in other concept cars, whatever you assume the fuel cell system costs, you'll obviously be saving a lot of money, and yet you'll get a better range, which is why we put such emphasis on the physics of the car, especially the weight. So I dare say that whichever automaker goes ultralight first to integrative designs is going to win the fuel cell race. Or to put it another way, an automaker doing research in fuel cell cars will do better to put its money into making the car lighter than trying to make the stack cheaper and the tank smaller, because they'll get to the same place with much less time, money, and risk. It's also important to understand that the platform physics is more important than the powertrain and is vital to its economics. If you consider 1 eta eta being efficiency, as the efficiency level of today's good cars, you might get 1.5 eta if you did as some BMW models do and burned hydrogen in an internal combustion engine, optimize the engine for that. If you made that a hybrid, maybe 2.5 eta. But if you make it ultralight, you're already at 3 eta. Hybridize that, 3.5 or 4. In fact, that 5-seat carbon SUV design I showed you a minute ago has the same mass and the same drag coefficient as my 2-seat aluminum Honda Insight hybrid. That's how light carbon is. Imagine being able to run a 5-seat SUV on a 1-liter engine. That's about what you could do this way. Best of all, of course, is to put it all together, put fuel cells in those super efficient bodies to get, in this case, a 6.2-fold efficiency gain. Remember that the aim here, when you think about whether hydrogen will work and pay, is not just to save fuel and pollution. There are strategic goals in automotive competitiveness, automaking competitiveness, plug-in power plants on wheels, getting off oil, being able to use any primary fuel to make the hydrogen, accelerating the transition to renewables. Hydrogen needs these very efficient vehicles a lot more than they need hydrogen. They can run on anything, but once you have the efficient vehicles, there is a robust business case for running them on hydrogen fuel cells. But meanwhile, there's competition from other more conventional kinds of powertrains. Here's a little example. There's a very good mature technology for very fast, small, light, cheap electronic valves, digital valves, which permit extremely precise control of both fuel and air injection under real-time closed-loop control. And that would enable you to make an internal combustion engine, even retrofitted with such a digital head and no cams, to do unusual combustion cycles, which are expected to be half again as efficient as a diesel, burning any fuel, including gasoline or ethanol, on the fly, with upwards of half again as much torque, but at least a third smaller, 10% cheaper, and extremely low emissions that don't even need cleanup devices. The first prototype of such an engine actually ran near Colorado Springs in late January and should be much further along by the end of the year from Sturban Industries, so watch that space too. And a little more about plug-in hybrids. Hybrids that have a bigger battery so that you can take short trips just on their electric range. The key, of course, to making this efficient and affordable is a light, slippery car. Plug-in hybrids can further improve the efficiency of the powertrain and can be comparable or lower in carbon emissions per mile compared to a fueled car. You can charge them with cheap off-peak electricity. You can sell their valuable storage back to the grid at peak hours, and under certain assumptions, this may be able to pay for the batteries. Plug-in hybrids, by adding off-peak storage to the grid, also greatly expand markets for variable renewables. You could sell an extra several hundred gigawatts of wind power this way. This does need a smart garage or its equivalent so that the car can talk to the grid properly, because the grid right now is not as smart as we would like. But here's what it could look like in California. Here's a typical summer load shape with the night trough and the afternoon peak. Now, if you put in 5 million plug-in hybrids, not terribly efficient, or 15 million super efficient ones, then you would fill the night valley, and all that extra is wind power that you could be using instead of spilling. And then if you use the distributed storage function to sell power back to the grid during the hot afternoon peak, when and where it's most valuable to do so, you can lop off that peak. Well, this would be a wonderful thing for utilities. Remember, cars are parked about 96% of the time. And the batteries or equivalent fuel cells in a super efficient light vehicle fleet would have 6 to 12 times the storage or generating capacity that's on the grid right now. So it doesn't take many people doing this vehicle-to-grid trick to displace the coal and nuclear plants, and roughly the first 2 million drivers to do this are going to earn back roughly the whole cost of their car. And because this suite of technologies can address the power plant 2/5 of the carbon problem as well as the transportation nearly 2/5, ultimately this can solve up to about 2/3 of the world's carbon dioxide problem. Utilities, of course, love the other way. They love the grid-to-vehicle model, which will work regardless. That's where you're charging the battery or plug-in hybrid vehicle, because they get off-peak electric sales. They may get to rate base some more grid expansion. They get to shift greenhouse gas burdens from the power to the transport sector. They may make money financing the batteries, and they can offer a high-tech customer a service bundle, including, say, more efficiency in your house and solar cells on your roof. That would be something to brag about. Now, let me talk a little about the competitive posture of the auto industry. This product is really incredible. We make one of them every 2 seconds. They're the highest expression of the Iron Age. It's a $1 trillion global industry. It's the most complex industrial undertaking in the history of the world. The most complicated mass-produced artifact in history. But it costs less per pound than a McDonald's quarter-pound hamburger. And it's quite durable and meets conflicting requirements with great skill. But there are a lot of reasons for fundamental change now emerging in this industry. Just think, it's got convergent products fighting for shrinking niches in a saturated core market at cutthroat commodity prices with stagnant basic innovation until quite recently, growing global overcapacity of about a third, forcing increasing consolidation. We're already seeing buyouts by private equity firms, and yet thin profit margins most of the time, limiting the attractiveness to investors and to recruits. It's kind of like airlines. It's a great industry, but a bad business. It's time for something completely different, as investors are now realizing. So, can we make this frog leap? The way we design cars now, because it all depends on design, is very incremental, component-level design, reasoning from the engine toward the wheels, emphasizing powertrain improvements, because that's where the losses are. The car is generally assumed to be made of steel, so it keeps getting heavier. And the design process is disintegrated, a whole bunch of specialists, 1,000, 10,000 specialists, in a huge group, each passing the baton to the next specialist, so the synergies get lost, you get institutionalized timidity, Baroque complexity, and that makes it hard. There's another way to design a car. On a clean sheet, whole system, from the wheels back, emphasizing great platform physics first, especially ultralighting, to maximize the snowballing of weight savings. Designing the car in an integrative, holistic fashion in a tiny group, maybe tens or 100 people, in a team play, not a relay race, capturing the synergies and boldly going for radical simplicity. That's also difficult. You know, Einstein said everything should be made as simple as possible, but not simpler. You only get to simplicity through complexity. We're now deep in the complex phase. It's time to break out into the simple phase. Einstein said, you know, I wouldn't give a nickel for the simplicity this side of complexity, but I give my life for the simplicity on the other side of complexity. And it's really time now to make the design simple. It's going to be hard to make a great car no matter how you do it, but I'd rather have it difficult because it's simple than difficult because it's complicated. Is Detroit ready for this kind of disruptive thinking? There's huge engineering talent there if it's unleashed. There's also really weak balance sheets, slow innovation, lots of rigidities, and a tendency to treat sunk costs as unamortized assets, as if it's better to write off obsolete stuff later when you don't have a company than now when you do. Obviously, we ought to be basing strategic choices on economics, not accounting, and it's important not to count cost per pound, as they normally do in Detroit, because nobody buys cars by the pound, buy it by the car. There's also incoherence in these businesses in which the lobbying and litigation arms tend to stomp on internal innovation and be directly contrary to corporate strategy. There are lots of examples of this. But I think these cultural obstacles are wilting under the force of what Schumpeter called creative destruction. It's a whole tsunami of change rolling over the industry, and that is what is going to change things in a hurry. Let me give you an example of an industry that did that successfully, and that's airframes. Boeing in 1997 was just where the big three automakers are now, and Boeing Commercial Airplanes made some difficult changes, including Toyota production system, and they got their costs back under control. But what was in the pipeline after the 777? What about growth? Airbus just 4 years ago was already outproducing Boeing, and some commentators were saying, is Boeing going to be around for the long haul? Their bold and quite unexpected response was a leapfrog, very efficient airplane, very simplified, saving a fifth of the fuel at the same price, half advanced composite by mass, a lot of advantages for customers. They switched over from hydraulics to electricals. They made a lot of things simpler. They cut the final assembly time from 11 days to 3. And this airplane has taken off in sales faster than any in history. It sold out till 2013. And now those radical changes throughout the integrative design are being rolled out to every model Boeing makes in the Yellowstone project. And that'll be across their whole product line before Airbus, which made mistakes in both strategy and execution, can get itself out of the ditch, and it may be too late by then. So could Detroit do, even to, say, mighty Toyota, what Boeing did to Airbus? Funny thing, we suggested in 2004 that Detroit think about imitating Boeing. 2 years later, the head of Boeing Commercial Airplanes became the CEO of Ford Motor Company. And he said, we can't do the regular Detroit turnaround thing where you just shutter a few factories and hope for a hit model. He said, we need to make completely different products in a completely different way. He arrives with transformational intent. And the automakers are increasingly open to basic change in manufacturing and materials. The dealers and the union are now pushing innovation as the best hope of saving this industry. And of course, the emerging prospects of leapfrogs by China and India and other new market entrants concentrate the mind. So this competition is going to change the automakers' managers or their minds, whichever happens first. And that's starting to happen. I'm very encouraged about it. Just a little about trucks and planes. It's the same story. Better aerodynamics, better tires, better engines, and so on, a bit less weight, not using exotic materials, but just so you can haul more stuff in fewer loads. And that will take you to a doubled, or with operational improvements, roughly tripled efficiency, and it'll double the big haulers' margins. Tripled efficiency gives a 60% internal rate of return. Here's what the supply curve looks like. And this is a big deal because heavy trucks use 1/8 of our oil, and it's the second fastest growing part. Now, again, the losses and savings multiply. Here's my pumping diagram from yesterday, where over 90% of the fuel energy at the power plant gets lost before you get flow out of the pipe. In the truck, it's the same deal. You start with a bunch of fuel going into a big diesel engine, and then you lose some more in the transmission and other powertrain or driveline components. And then 2/3 of your losses over the road are in aerodynamics and about 1/3 in tires. And you end up with only 6.5% of the original fuel energy actually moving the cargo, another 4.5% moving the truck. So if you reduce the aerodynamic and tire drag by 50% and reduce the idle time 80% by putting in an auxiliary power unit, so you're not idling this giant diesel all night to run your radio and air conditioner, you save half the fuel right there. That's not hard. And you can tunnel through the cost barrier because as you go through these improvements in tires and aerodynamics and engine and so on, you end up with smaller engine, smaller fuel tanks, more stuff hauled, and you end up with superior economics. Same story that we've heard for buildings and industry. In airplanes, it's much the same. The 787 showed that the first 20% fuel saving is free. And if you look at the efficiency of various airplanes and of the fleet, with and without squeezing out empty seats, for some reason the government predicts that this progress we've seen consistently is going to continue, but only half as fast, which seems odd in a pricier oil world. But we found, the same as a number of industry studies, that you could double or triple efficiency with the same kind of prescription: advanced composites, new engines, better aerodynamics, better integrative design, and accessory loads. And there are a lot of conservatisms in this. We're not counting other things that are coming at us from the lab and look very promising indeed. In fact, a lot of what we're trying to do in these planes was already invented, guess what, by nature. Here's a California condor exhibiting, according to the great engineer Paul McCready, who should know some of the wonderful technologies that we need now to put into airplanes, including, if we really get good at it, advanced manufacturing techniques. Hatch out our airplanes from big eggs. That would be really neat. I think the bird's smarter than we are about that part. And there is, by the way, a world for airplanes after kerosene. We didn't assume this in our efficiency analysis, but you can actually do quite well with liquid hydrogen. It's bulkier but lighter, and everyone who's tried it, all the main airframe makers and NASA agree that it's safer than kerosene in a crash. It's been tested by a number of folks, and Boeing found in a typical, say, 767 class, counting proper interactions within the design, that when you net out all the good and bad effects of switching to this bulkier but lighter fuel, you get about 10 or 15% better energy efficiency, which is about enough to pay for liquefying the hydrogen. So it's pretty much a wash on net energy compared with kerosene. It's obviously much cleaner, although you are putting water vapor high up, so you may not want to fly all the way in the stratosphere, but just below the tropopause. Another good thing you can do besides jets is to use fuel cells for propulsion. There's both NASA and Dutch work suggesting considerable efficiency gains, even a doubling for smaller aircraft, having basically very sophisticated electric turboprops with superconducting motors running on liquid hydrogen. And that's another 20 to 50% fuel savings beyond our analysis from that change in fuel. It does pay to be bold in all these kinds of savings. If you use Academy kinds of 10 or 15-year-old technologies, you'll save a quarter of the oil in the country across all the range of end uses, transport and otherwise, and it'll cost you about $6 a barrel. But if you use the more advanced techniques I've described, which are already being surpassed by new developments in the last few years, you save half the oil at $12 a barrel. And that's a better deal, because if you didn't do that, some of the supply substitutions for the other half would cost too much. Now, just a word on the supply substitutions themselves. We are often told we'll need lots more liquefied natural gas to keep up with growth in gas demand to 2025. So the LNG is the red part. However, we could save about twice that much gas just by using electricity more efficiently, especially at peak, where we make it inefficiently in gas turbines. In fact, they're so inefficient that if you save 1% of our electricity, including peak hours, you thereby save 2% of the gas in the country and cut its price 3 or 4%. So if you combine that with garden variety efficiency gains in buildings and industry and some gas displaced in refineries and such, you end up with 10 or 12 trillion cubic feet a year of gas that can be substituted for oil or made into hydrogen. Now, the biofuel side of the supply substitution, I'm not talking here about corn ethanol, which is a small, slow, costly, heavily subsidized resource, although improving. Rather, I'm talking about making ethanol and other things, maybe butanol, out of woody, weedy stuff like switchgrass and poplar, which gives you about twice the yield, less investment, up to 8 times better net energy yield, with some left over beyond 4 million barrels a day of fuel to displace petrochemicals. And Brazil has already gone oil independent on the basis of offshore oil, plus displacing a quarter of its gasoline in energy equivalent with sugarcane ethanol, which started off with a pump priming subsidy that they've gotten back 50 times over. It's now very competitive without subsidy. Sweden is headed off oil by 2020 via cellulosic ethanol based on forest waste. Europe is a much bigger producer than we are of biodiesel. Over half of it's sold by oil companies, and it's their way of shifting farmers from temporary subsidies to permanent revenues. Now, here's how all the moving parts fit together in winning the oil endgame. Instead of needing 28 million barrels a day of petroleum products in 2025, we could by then have displaced almost 8 with efficiency at $12 a barrel and still be in the process of implementing the last 7 worth of savings. So not having done that part yet, we'd still need 20, of which we could get almost 6 from biofuels and the like, almost 2 from the no-brainer substitutions of saved natural gas that make sense at any price, almost 8 from projected domestic oil output from areas already allowed, and we'd still need 5 from somewhere. Where could that be? Well, maybe we should buy more efficiency, it's so cheap, or wait a little longer and get the rest of it that we're still implementing by turning over the rest of the vehicle fleet. Or we could still buy oil from Canada and Mexico, or by then the World Trade Organization, probably long before that, will have made us drop our illegal 100% tariff on imported Brazilian ethanol, which is making them send it to Asia instead of here, which is a lot closer. This is to protect our corn farmers, of course. Or, oh, wait a minute, I haven't yet accounted for 2/3 of the saved natural gas, and that would be enough if directly substituted for oil to cover this whole balance term. Or we could use that saved gas even more profitably to make hydrogen, which is more efficient in use and therefore could also displace all the domestic oil. Imagine being a net oil exporter again. And I'm not counting other options. For example, there's enough available windy land in the Dakotas to make enough hydrogen cost effectively by then to run every highway vehicle in the country at these levels of efficiency. So lots of options. And you can actually turn over the vehicle fleet quite satisfactorily with some policies we propose to speed it along. So we get rid of the unimproved vehicles pretty quickly and jump over a brief interval of incrementally improved vehicles as we tooled up to make the tripled efficiency ones, maybe even better stuff after that, and they would pretty much capture the whole market by 2040, saving about $400 billion at the pump at $26 a barrel. Now, big changes have happened quickly, even in this industry. It took the auto industry 6 years to switch from wood to steel auto bodies back in the 20s. It took them 6 months at the start of World War II to switch from making cars to making the jeeps, tanks, planes, and munitions that won the war. Boeing transformed the way it makes planes in 4 years, and they went from behind the 8 ball to having Airbus on the ropes in 2 or 3 years. Amazing turnaround. GE's small team took the EV1 battery car from launch to street in 3 years. Now, normally, if you wait for normal technological diffusion through normal market mechanisms, it takes about 12 to 15 years to go from 10 to 90% adoption in the stock. But we figured out some policies that'll get to that 10% takeoff point about 3 years faster. It is encouraging that the last time we paid attention, we were saving oil per dollar GDP over 5% a year. It's like a Gulf every 2.5 years at a given level of economic output. The biggest contribution to that was almost a 5% a year gain in the efficiency of our new American-made cars, 96% for making them smarter, only 4% for making them smaller. And as a reality check, if every light vehicle on the road in 2025 were only as efficient as the best hybrids in the showroom in 2004, they would save twice the oil that we now get from the Persian Gulf. That doesn't sound very hard, and that excludes all the continuing rapid innovation. There's another dimension here I want to highlight, and that is the emergence of military energy efficiency as a major driver of civilian energy efficiency. There are things called strategic vectors in the military. These are disruptive changes that drive the revolution in military affairs. And we've had 4 already: speed, stealth, precision, and networking. The next one to come at us is going to be called endurance. And that's the ability to stay out there a long time doing dispersed operations over big areas without dragging a heavy fuel logistics tail behind you. The Department of Defense is very handicapped now by half-century-old way of getting and using energy, designed for massive steel forces that, I think as Lord Curzon said, floated to victory on a sea of oil. In World War II, 6/7 of the fuel that defeated the Axis powers came from Texas. Today, warfighting uses 16 times more oil per soldier than it did then, and Texas is a net importer of oil. Today's warfighting needs exactly the opposite of what the legacy force needs. We need an incredible amount of agility, mobility, maneuver, range, persistence, and so on, via much greater endurance. And that fat logistics tail to supply the fuel is 70% of the tons that the military moves around, and logistics, moving stuff around, takes half the people and a third of the budget. And this is now a magnet for insurgents. It's a big risk in military operations, and it's very expensive in lives and treasure. So the department now realizes it needs less or little or no reliance on those long fuel supply chains by greatly improving its fuel efficiency, and that means designing things differently. So far, to get inefficient platforms, although capable ones, they have assumed that fuel logistics is free and invulnerable. That assumption is going to change, and because there's a major shift now emerging toward military energy efficiency. And here are some of the technologies that have been popping up. Look at the increase in combat effectiveness and the decrease in fuel right across the board. Land, sea, and air platforms. Even forward operating bases that use 95% of their genset fuel to air condition the desert. Those are air conditioners ducted into uninsulated tents. And there are ways to keep people comfortable in the tents with little or no electricity. The list goes on like this, but you get the idea. This is not a trade-off between combat effectiveness and energy efficiency. It's energy efficiency and the technologies that yielded producing major gains, often revolutionary gains in combat effectiveness. And that makes it an easy sell to the warfighters. Now, suppose that we use these advanced materials and propulsion systems, for example, to find that Saudi Arabia under Detroit and Seattle. And suppose the Department of Defense were doing the same thing to transform its forces to save billions of dollars a year, hundreds or thousands of lives, tens of billions of dollars a year in fuel logistics costs. Well, the key science and technology investments and procurement actions needed to do that could catalyze the transformation of the civilian car, truck, and plane industries, exactly as happened when military R&D created the internet, the global positioning system, the microchip industry, and the jet engine industry. And it's a big prize. Negagulfs, a world that doesn't care about oil and doesn't have to fight over oil. A competitive auto industry, cheaper oil, rebalancing American trade, global development, diplomacy. To be sure, we'd become more competent, more capable, more confident warfighters, but we'd have a lot less need to fight wars, particularly over oil and the instability it brings with us. It would be a safer world, and the Department of Defense's greatest ever contribution to its national security mission. Many people there now realize that. The speed of implementation I proposed is quite reasonable, looked at historically. Here's how fast we improved light vehicle efficiency. Here's how fast our analysis assumes it would continue to be improved. Not hard with these much better technologies. And implementation's already underway via institutional acupuncture. We figure out where the business logic is congested and not flowing properly, and we stick a needle in it. Most ambitious thing we've undertaken, and it's going well. We need to shift behavior in 6 sectors. Aviation already underway. Heavy trucks led by Walmart. Based on our analysis, they are requiring doubled efficiency trucks of their suppliers. That demand pull brings those trucks into the market where everybody can buy them. Military emerging as the federal leader this year in getting the country off oil. I'd say we're past the tipping point in those 3, and there's strong investor interest and activity in fuels and finance. There was $71 billion of private investment in the clean energy space last year alone, worldwide. The slowest, hardest, but now rapidly changing sector to shift is going to be cars and light trucks. But I think that move from Boeing to Ford, the dealer and union support, the creative destruction pressure, the leapfrog prospect abroad is producing very rapid change. There have been some skeptics about this, but they're starting to pay attention. And I'll end with a couple of little other thoughts. The same innovations apply to public as to private vehicles. We did not assume any shift to public transport, but you could do a lot of really neat things with these technologies. In fact, just with ordinary materials, ultralight rail looks many times cheaper than conventional light rail and can go anywhere from 150 mile in the intra-city, like here to LA, or right downtown, right over the median of existing roads with 2 lanes overhead, replacing 4 saturated highway lanes. Curitiba's surface subway, now imitated in 84 cities around the world, beats cars hands down. A lot of people get out of their cars to ride the kind of surface subway bus system, express buses, because it's faster, cheaper, safer, more convenient than driving. The Dutch have been inventing a superbus for the Beijing Olympics. Think a triple stretch limo made of carbon fiber with great aerodynamics, a lot less energy than a TGV train or a maglev levitated train. Runs down ordinary roads. The solution, of course, to our transport woes is not just technical, because transportation is a means. It's not an end in itself. What we're trying to do is get access to where we want to be. The best way to do that is to be there already, so you don't need to go somewhere else. That's called sensible land use, or as they say in Europe, spatial planning. Next best way is to move the electrons around and leave the heavy nuclei be home. Third best way is, if you have to move your body around, there are lots of ways to do it. All those who believe in individual mass transit, raise your right foot. Have a personal vehicle, even a hybrid bicycle, a shared personal vehicle, a public vehicle. How far does public policy let all these ways of getting around or not needing to compete fairly, and not just transport modes? If we stopped subsidizing and mandating sprawl, wouldn't we have a whole lot less of it? What if drivers got what they paid for, which I think they do, and paid for what they got, which they certainly don't? Most of the costs of driving are socialized. We don't have ways for trips and negatrips to compete fairly, but we're starting to. These are all key questions. My focus here, of course, is on vehicle technology, because the whole system efficiency potential is enormous, and if you combine it with these other ways of not having to travel so much, so if we have great cars and need to drive them a lot less, we will be in much better shape. This is like an endless onion that you keep peeling, only without the tears. If you look at transportation demand management, mode switching of all kinds, vehicle sharing, mobility and access-based business models, and mandating and desubsidizing sprawl, there's at least an order of magnitude efficiency gain to be had there collectively, besides, or going beyond just the 4 to 6-fold better cars. Same in aircraft, 2 or 3 times, maybe 4 or 5 times with hydrogen, more efficient aircraft, but also big operational gains at the airport and the systems levels, and with point-to-point GPS-controlled flight in smaller hubless aircraft by getting real competition for gates and slots. Air taxis, mobility and access-based business model, again, virtual mobility, another order of magnitude there. And the same with efficient trucks when you start getting into not just modal switching to trains, maybe even containerized airships, but also enormous logistics improvement. These are just the things we can now clearly see as profitable and practical. There will be more innovation to come. The time to reinvent the wheels is here, and it's happening, because sometimes one must do what is necessary. Thank you.
The questions tonight are really terrific, and I am going to work with the organizers to make sure that the ones I don't get to get posted, and that Amory is compelled to answer as many as possible, so he doesn't think he can get out of it simply by running a little long in his lecture. Now, on the matter of, a number of you, by the way, want to know, since not all of you were able to absorb every element of every one of Amory's slides, you'd understandably like to know where you can get them. I'm assured that we'll be up on the RMI website within 2 weeks. That's rmi.org, which is the answer to all of you who want the best website to go to for further information on this subject. The podcast of this event, just put your email address in one of the bowls out in the lobby. You'll be notified as soon as that's available. Now, Amory, let me begin with some interesting specifics. On the issue of safety, You're going to be selling us 200-pound cars, and a number of people in the audience would like to know how they handle up and down hills and in snowy, windy, and muddy conditions, not unlike those you are accustomed to finding in Old Snowmass, Colorado.
Just fine, thank you very much, because they will have, as to traction, very fast, precise servo motors on every wheel under real-time closed-loop control. And generally, when you have very light vehicles, you have harder, higher pressure, but narrower tires, which in effect cut into the snow better. And the traction is similar or better because the contact patch is smaller, so the less weight distributed over less area gives you the same or better traction. Of more interest is the handling in crosswinds, and that you design partly by what amounts to automatic yaw control. The car will go in the direction in which you point it with the side stick, compensated already for wind and camber. But also, you do a lot of the trick with advanced aerodynamics, and it's not that hard. If you were to look at the front end, just head-on of that hypercar Revolution concept vehicle, you'd see that the sides come up, and before that curve goes into the roof, there's a little 2-millimeter step down, the purpose of which is to trip the laminar flow of the wind into turbulence, detach it. So, you know, most of the reason the car would normally yaw off this way is not that the wind's pushing on this side, which looks pretty slippery, but it's sucking on the other side through the Bernoulli effect. So if you detach into laminar flow, it doesn't do that anymore. And the proof of the pudding is that the sunrace vehicles that compete going between Darwin and Adelaide across Australia are passed in the other lane by 100-mile-an-hour super heavy truck multi-stage caravans, land caravans that would normally risk blowing an ordinary car off the road, but these little ultralight airfoils go along just fine because they're designed to convert that crosswind into either neutral or downforce.
Amory, how does the strength of your thermoplastics hold up when defects are introduced? So what if when Thomas Friedman was hammering on that convex sphere, there'd been a hole drilled in it?
They do quite well, and this is part of why they're used extensively in military structures that need a lot of battle damage resistance, because the strength is not just in one place, it's distributed throughout the structure in zillions of fibers that are finer than hair but stiffer and stronger than steel. Obviously, if you drill enough holes in carefully chosen places, you can cause it to fail, as with any structure, but it's unusually resilient in that regard.
With the weight-saving strategy, which you emphasize so strongly in vehicles, how does that help with heavy trucks where cargo dominates the weight so strongly?
Well, there are two kinds of heavy truck loads, those that run out of volume first, like potato chips, and those that run out of weight first, like bricks. Obviously, if you are going to weigh out before you cube out, and there are a lot of loads that do so, then you're better off making the truck lighter so that you'll haul more payload per load. A friend of mine that's in the trucking business has done this to his own trucks, and he routinely hauls in, say, 3 loads what his competitors haul in 4, or 4 and 5, and guess who wins the low bid?
Amory, this questioner, in looking at your graphs of progress in reducing oil dependence during the 80s, draws the conclusion that the oil-producing states stopped progress in the 1980s by dropping the price of oil and effectively inhibiting innovation and progress. What is different about today that will prevent this from happening again?
The big difference is that the, well, let's see, let me start with a small difference, which is that now oil prices come from a tighter market where price is determined largely by the cash flow requirements of certain leading exporters, like Saudi Arabia and Venezuela. But, of course, markets will clear at lower prices if you have less demand. And indeed, the policy conditions that created the mid-'80s price crash in the United States in energy have now all been put back in place, so we could see that very bad movie all over again. But the big difference is that now it's not only energy prices that compel our attention to these opportunities, it's also competitive strategy, climate, and the nest of issues loosely called security, which includes geopolitics, international stability, war and peace. And I think those issues will persist regardless of what energy prices do until we really solve this problem.
Another skeptic, Amory, notes that public apathy, foot dragging, car companies, and other factors killed the zero-emissions vehicle mandate in California, despite the higher efficiency of electric cars.
And the CEO of GM now says that's the biggest mistake he ever made.
So how do we run this play again and succeed?
By not relying on regulation to make markets, rather providing superior cars that will sell because they're better. And engineers are raring to go on this because they know how important it is for their company's survival and how much fun it will be for them, how rewarding personally to design great cars in a whole system fashion.
And of course, Amory, in a Palo Alto, Stanford auditorium, you are inevitably going to be asked your opinion of Tesla's plan to build a fleet of electric cars as a part of the oil use solution, and your views as to the relative merits of battery-powered cars versus fuel cell-powered cars more generally.
Well, if you start with electricity, perhaps from wind power, say, it is obviously more efficient to run it through a battery to the wheels than to run it electrolytically into hydrogen and then through a fuel cell to the wheels. I wouldn't actually make the hydrogen that way, at least for the next decade or two. I would make it out of natural gas, which, even if you don't capture the carbon from the forecourt reformer, and there may well be ways to do that, will still emit 2 to 6 times less carbon per mile than what you're running right now. Tesla is a very capable outfit, and I think with engineering geniuses like J.B. Straubel will demonstrate.
Educated where again, Amory?
Educated here, thank you. Will demonstrate and is demonstrating that if you get the physics of the car right and use advanced propulsion, you can do even better than the EV1, which was the best battery electric car of that time. In fact, a guy on my staff designed its battery pack, so I think battery electric cars will turn out to be a larger niche market than one might have supposed. Nonetheless, they probably won't in the short run make a large niche. I think the company can do well with good execution, but there are still people who will want to haul a lot of stuff for a long distance, and even very good batteries have an order of magnitude less useful energy per pound than fuel does. But whatever your propulsion system and however the market determines those market segments, obviously you will do a lot better with a light slippery platform than a heavy draggy one, and that's one of the most important lessons that Tesla's success is going to show.
Amory, the half of the audience that owns hybrids, of course, wants to know how they should drive them, since you've twice told them to pay no attention to Consumer Reports. And the other half of the audience wants to know if they want to buy a car now, what should they buy, or should they continue to drive their clunkers for a couple of years and wait for something better?
Boy, that's a hard one. That's like saying, I need a computer or I need some other consumer electronic gizmo. Should I buy it now or should I wait because I know every few weeks something better, cheaper, faster, smaller is going to come out? I guess not smaller in the case of a car, but when you buy it, you need it, or the other way. Sorry, when you need it, you buy it, and then you will. It'll keep getting better, but at least you met your needs, and you'll be satisfied with what you get, I think.
And the best source of advice on what they should buy?
Well, if I were buying a car now, unless I want to be a really advanced customer and go for, say, a battery car or soon a plug-in hybrid from a major maker, so I'm sure the software will work right, I think I would buy a hybrid, and there are, 9 hybrids on the U.S. market. There will be 20 probably by the end of the year. So quite a good choice. Your dealer would like to sell you a hybrid. They make twice the margin on them than they do on comparable non-hybrids. And I would go for one with better physics, one that is lighter and more aerodynamic. Now, as to how to drive the hybrid, we've had 2 pieces on this in the RMI newsletter, and there are 2 main elements to it. The more obvious one is that if you're going to slow down or stop up ahead, like you see a red light in the distance, start gently braking early so that you will recover as much of your momentum as possible back into the regenerative braking system, which, as I mentioned, is 2/3 efficient. And then you can reuse that energy for acceleration and hill climbing later. And in fact, by slowing down a little early, maybe the light will have turned green by the time you get there and you won't have used up all your momentum and you can just speed up again. The less obvious element of driving a hybrid efficiently, especially the Toyota varieties, is to accelerate briskly, not gently, up to cruise speed. And the reason is that the most efficient operating point for the engine is at rather high speed and torque. That is up toward the upper right of the engine map. So you will use less fuel getting to cruise speed briskly for a short period, not quite flooring it, but most of the way there.
Every teenager in the audience, Amory, is delighted with this news.
Then getting there slowly for a long acceleration. This is, of course, exactly the opposite of Consumer Reports advice and the opposite of what they taught us in driver's ed a long time ago.
And Amory, in the realm of first-name celebrities, the audience wants to know if you're talking with Governor Schwarzenegger.
Haven't yet. I've met him very briefly.
We'll see if we can make that happen as quickly as possible. Will you
Thank
join
you.
me in thanking Amory Lovins?
Thank you.
Oh